From last 3 lectures, we have obtained an adequate understanding of the central step of an electrochemical reaction, the interfacial electron transfer. So this allows us to predict the current potential behavior. To measure such a behavior in practice, in the field of fundamental electrochemistry, we usually use the 3-electrode cell, which is potential-stated. And in fact, what we measured in many cases are not what we predicted if we only know about the central step. Therefore, it's important to have an overview of electrode processes apart from the electron transfer and be aware of the complexity of molecular motions at the electrode solution interface. A very brief figure of 3-electrode cell is provided on the left, and I will discuss these electrodes in terms of their purpose and requirements. The working electrode, as its name implies, is to probe the reaction of interest, so it's required to only induce the reaction of interest without inducing any other reactions. And the reference electrode is to provide a reference level, and for the potential difference between the reference and working electrodes to be actually readily measurable, as discussed in the first lecture, and is required to have a constant and stable, or at least predictable, potential. And the voltammeter is connected in between the reference and working electrode to measure the potential difference. A counter electrode is usually additionally needed to conduct the current of interest through itself, so it's required to have a large enough surface area and needs to be chemically inert. More specifically, the reason why we need a counter electrode to conduct the current through itself rather than through the reference electrode is for the potential stat to precisely control the potential of the working electrode. Let's look into the potential difference measured by the voltammeter, which equals to the interfacial potential difference of the working electrode plus the potential drop across the solution phase, and subtract the interfacial potential difference of the reference electrode, where the potential drop across the solution phase is more precisely the current flow through the reference electrode times the resistance of the part of the solution in between the working electrode and the reference electrode. So the introduction of counter electrode into the system guarantees the current through the reference electrode is negligible, which not only assures a constant and stable reference potential of the reference electrode, but also keeps the ohmic drop through the solution phase at minimum level. It's often true that the current through the reference electrode in the 3-electrode system is far less than 10 microampere, and the ohmic drop across the solution phase is smaller than 100 ohm, such that the ohmic drop through the solution phase is well below 1 millivolt, and then this is not important to worry about. Alternatively, if the working electrode is a microelectrode, then the total current would be in the order of nanoampere, and in this case, the counter electrode may not be needed. In many conditions, actual measurements give us a dependence of current on the electrode potential that is not simply logarithmic because of the involvement of other electrode processes apart from the interfacial electron transfer. So it's necessary to have an overview of what is going on at the electrode solution interface. The figure I show here presents such an overview. But I would first remind that the scenario here is completely different from that for introducing the electrode double layer in the second lecture, where the whole system is at equilibrium, but here an electrochemical reaction already starts. Overall, it's often true that the electroactive species is depleted at the electrode surface or around the electrode surface, while more and more materials are supplied from the bulk solution by the mass transport. But if we look closer into the electrode surface region, there's very likely other electrode processes that are non-Faradic. For example, the double-layer charging I mentioned in the second lecture, and it's not included here. It always occurs. And sometimes there may be physical adsorption and desorption of reactive species, and it's also likely that there are some coupled chemical reactions either before or after the electron transfer. Some of these processes may have a rate constant that is potential dependent, so finally depending on which step is the rate determining step, the measured current potential relation may be altered in different ways due to the involvement of these additional processes. Therefore, we can see that sometimes it can be quite complex of what's going on at the electrode solution interface.